I have some sad news. Today is in fact my last lecture with you for 2 weeks, but I have some good news to go along with it. The first piece of good news is that I'm going to bring back some swag from the trip in America, particularly for those of you who participated in the puzzle hunt. So look forward to that. And the second thing is you're going to get a chance to be taught by Dr. Jianzhong Qi, who's fantastic, and it's something you should really look forward to. Our styles are very different, and so it's pretty healthy partway through semester to get a different person's view on a lot of the same material that we've been doing. So that's something to look forward to for the next 2 weeks of class, and then I'll be back with you for the very last week and for your graduation from FOA. So all exciting things in our future. For the last 2 lectures, we've been talking about linked lists, and today we have just a small bit more to go through on them. Perhaps look at a little bit into how efficient they are, and particularly how we can extend our basic idea of a linked list to improve some of the operations that we've been doing thus far. Then after that, we'll probably get onto a new data structure if there's time, and then a bit of a wave goodbye. Our first question for today is how long does inserted n take? And given that we're still warming up, I won't come into the audience to prey on any of you. But we will go back to our code to have a bit of a reminder. So our inserted end function that I devised here was really the same as insert at index, inserting it at the index, the very last index possible, which was the end of the list. So if the list is of length n, let's check out inserted index and see how long this would take. So inserted index starts off at the head of the list. That's the first argument that we give it. Starts off at the head of the list. And then until you get to right before the index at which you want to put it, keep iterating along, following the pointers along, going to the next element, to the next element. And if our list is of length n, we're going to have to go all the way, bounded by the length of the list, to get to the last element in order to put our new last element there at the end. So an insertion is not going to be very efficient because we'll first have to traverse all the way to the end of the list. This is in contrary to our array way of implementing this kind of data structure, in which if we knew where the end of the list was, we could just pop a new item in that index. But I forget who it was. It might have been Vincent. Was it you at the end? No? I forget who it was in the last lecture. Someone said that, oh, why don't we instead keep track of how long the linked list is and keep a pointer to the end of the linked list. I forget who it was, but one of you guys is so smart that you managed to preempt today's discussion. But yes, it's true. If you keep both a pointer to the head of the list and to the tail of the list and update both of them accordingly when they need to be done, if you want to insert something at the end, you can jump right to it, just like we did with arrays, because you're always keeping track of where that tail is. As well, keeping track of the size of the linked list could be useful if that's going to be a call that you'll make frequently, because every time you add an item, it's very, very cheap to increment that count by 1, and every time you remove an item, it's quite cheap as well to decrement that counter by 1. Much, much cheaper than iterating through the whole list to figure out how long it is. So there are a few different ways that we can improve the construction of our linked list to make it a little more flexible. As well, we saw we had quite complex code when we wanted to do that pop operation where we got the stuff back. We had to have pointers to pointers, and then the actual code got a little complex. So to help ease some of this burden, we have created for you, and for you to review, a bit of more sophisticated code to do linked lists that expands on our original version that we've been looking at thus far. And this is in 2 different files. We have list.eg, which is an example of how to use our new linked list code, and we have listops.c, which is going to be the code implementing the linked list itself. And let me scroll back up to that. Let's look at how we use it first, and then we'll go into the implementation. After all, we're now talking about abstract data structures, where the thing we care about more is the functions that are available to us than the way they're implemented. Ultimately, the way they're implemented is important because that determines the efficiency and runtime and memory characteristics of our abstract data structure. But as an end user, as a programmer who's using these structures, at the end of the day, the most important thing is going to be, does it actually do the functions that we're asking of it? So that's what we'll look at first. In list example, we now have access to a function that's included in this file, listops.c. We have a new function, makeEmptyList. That seems fairly straightforward. And then we get a list T object, which I will presume is also going to be in listops.c. To tell our program what kind of object is going to be in the data of our linked list, as before, we have a typedef, and we're putting it here in this file instead of in the file that contains the linked list implementation. This makes sense because we probably don't want the way we've implemented the linked list to change every time you want to use it, including if we have two programs. In one program we want to use our linked list implementation for integers, and in another program we want to use it for strings. It makes sense that we should have the same code file that can be reused in both of these, like a library. And in one of them, when we use the library, we'll tell the library that we want to use it with integers. And in the other case, we'll tell it that we want to use it with strings, or with students, or with whatever object type that we want to use. Once we've made the empty list, we're going to read some things in from the terminal, insert some things at the head, insert some things at the foot. If you'll notice here, we're actually reading in an integer, so we're going to add in the integer itself at the head. We're going to add the integer +1 to the head, and then at the foot, we're going to add the integer +2. Then while the list is not empty, we're going to get the head of the list, print it, and then set the list to be the tail of the list. And we'll see how this works in a moment. And when we're done, print a new line and free the list. So some basic list operations. Let's give it a run, and then we'll dig into the implementation. And this is called listeg.c. It's going to ask me for an integer. It's going to ask me for another one. Let's put in 10, and we'll just leave it at that. You can see that the first thing added to the list was the number 1 over here. And then after we added the number 1, we inserted 1 plus 1 to the front of the list. And then once we did that, we inserted 1 plus 2 to the tail. The next thing, I entered the number 10. And so the number 10 got put at the head of the list. Then the number 11, which is 10 plus 1, and then 12 got put to the back. And then all we did is access the elements of the list. Let's peek at the implementation now and see just how it's doing it. We'll start with make empty list. The first thing you'll notice is that we have a new list T type over here that contains a pointer to the head and a pointer to the footer. But inside our list EG, we never had to use head and footer explicitly. I didn't type head here or foot here. I just typed list. The reason I could do this is because this function already knows that it's expecting a list structure, and inside the list structure, it can access the head if it wants to, and it can access the foot if it wants to, helping the programmer to save some brain power in having to keep track of the head and tail themselves. This is another example of abstraction, the powerful technique that we've seen to hide some details from you during the course of your programming to make your life easier. So some work ahead of time to make a more sophisticated structure has actually saved you complexity later when you come and try and use that structure. Back in list ops, we now have make empty list, creates a new list T pointer. We malloc some memory of it so that we actually have a place to store these two pointers, the head and the footer pointer. We check if the malloc succeeded. At the very start, with no items in the list, both the head is null and the footer is null. There's no objects there yet. And then return the list, which is a pointer to one of these structures. Is empty list also pretty easy? We just check if the head is pointing to null. Free list is very similar to what we saw yesterday. We have, just like I had old and p, instead we've renamed them current and previous. Previous is going to be our old pointer from yesterday's code. First, check that you're not trying to free an empty list. Start at the head of the list, and then go through each of the items, figure out what the next one is going to be, and put that in current. Make sure you've saved the one before, and then free it up. Now we're at insert at head. We're going through these one by one. There's really nothing particularly new here. It's just the same thing we've seen before, wrapped into another layer of abstraction. So it takes in our list. It takes in value, which was previously called stuff in our prior examples. Creates a new node, and this is the first time we're now seeing a node for the list. But the node is exactly the same as the node we used before, only it's now going to be used within this larger list T structure. So head is going to point to a node, and foot is going to point to a node, and then each node will also point to the next node along, just like the same linked list structure that we've seen before. So back to insert at head, create a new node, check that the memory allocation has succeeded, put the data that we want to put inside the node, and then make sure that the new node points to the old head, and then change the head so that it points to our first item. Again, we can see this on the iPad quite simply. If this is, that is head, and we come along and make a new item. First, shove the data, let's put some data in there. First thing you do is you put some data in your new node, then you attach a pointer to the old head, and then you change what head is pointing to, because that is no longer the head. This is now the head. I've said it in both lectures prior in this week, but I'll say it once more. The best way to understand the code is to do these same kinds of diagrams that I'm drawing. Go through the code, figure it out, draw a little picture, draw some nodes in, and actually explore for yourself what the code is doing. Insert at foot. Nothing particularly special here either. Same thing once more. I will walk through it just to give us some more familiarity. Create another node. Check that the memory allocation has succeeded. Put some stuff in it. Because this one is being put at the end, the tail should always point to null, and so we've got to put a null pointer in there. Make sure that the list isn't already empty. This would be the case if the footer was null. So this would make this the very first thing in the list. If it's the very first thing in the list, just set the head and the foot to this new thing. Otherwise, look at what was previously the footer and make the thing at the foot point to your new node, and set the new foot of the list to be the item you just ended. We'll do our diagram for this. We have our foot here, and we create a new node, we put some stuff in it, we attach a pointer from the old foot over to our new thing, and then we move the foot pointer over to here. Ta-da! Now we're almost there. Get head, exactly what you'd expect, returns the data in the head, and also checks that it actually exists, otherwise it throws an error. And get tail does something very similar. And we will leave it at that for our linked list operations. I'd encourage you to download the code. It reminds me, I still haven't put up the code examples from yesterday. We'll get there. But these two examples are already up online. I encourage you to download them, play around with them, and also feel free to use them in your code. Just remember to cite them appropriately. There we go, the curse of the missing clicker. Our question was, can we get O of 1 insertions to the end of the linked list by storing some extra information? Our answer to that, yes, we could do that just by keeping track of where the foot was. Here's a summary of what we've seen with our linked list and arrays and our pointer implementation and our array-based implementation of a linked list structure. Now, typically, the reason I'm kind of getting caught up on my words here is when people say linked list, they typically refer to the pointer implementation, even though in one sense a list can be implemented either using pointers or the array. So watch out for that when you're speaking to other computer scientists about this. We'll go over this quickly. To access the kth element in an array, if you know I want to access element number 5 in an array, you just write the name of the array and then number 5, and it goes to it directly. However, if you want to access, say, the 5th element in the linked list, you have to start either at the head or the tail, and then go 1, 2, 3, 4, 5 from the start, or if you know how long the list is and where you are at the end, you just do the reverse and count backwards. So that takes O of k, where you want to access the kth element, assuming that we're going from the start. And if there are n elements in the linked list, that's bounded by O of n. It's on average going to be faster than O of n, but O of n is a good bound for it. Adding something to an array, if we want to add something to, adding something to a list that we're implemented using an array required us to do this, put something, copy everything over and then put something at the start. So because we had to move everything else up by 1, that was O of n. And with a linked list, it was just add one thing to the front and then reattach the pointers. So that was O of 1. Pop, same kind of story. You have to do your copying over depending on exactly how you've set things up on your, in your array. Insert at end was pretty fast for both of them, because if you know where the end of the array is, you just put a new item in there. Likewise, for the pointer-based version of linked lists, you just add your new item, attach your pointers to it. And then inserting at the kth position is O of n for both of them, but for an array, it's O of n copies, because you're still copying over a whole bunch of elements. Whereas for the pointers, it's just navigating to that position, which is bounded by O of n, but you don't need to then copy everything along. So it might end up being substantially faster, even though formally the runtime might not look very different. So that just about covers it for our segment on linked lists. Lists, stacks, and queues are all the examples that we've seen of abstract data types. They're not actually something that you can physically check inside your computer like an integer is. If we want to measure an integer in a computer, we can measure those electrical pulses and convert those electrical pulses pretty directly into a string of 1s and 0s, and the 1s and 0s are our integer as long as you read it correctly. But a linked list is not physically in the computer, you can't measure it. It's stored in the representation of the data. It's how we think about the memory that we have stored. This is why it's called an abstract data structure, because it takes some way of storing things and creates a mapping, some metaphor, between what we've actually stored in our computer and the way that we envision and think about it. So all the pretty pictures we draw using nodes and arrows, that's not inside the computer, that's inside our minds. And the tool that we have, abstraction, which is really the key idea of the course here, is to create these mappings, and they're very, very powerful. The same thing goes for stacks and queues. Stacks and queues we saw that were really just linked lists. But by taking our linked list and saying, okay, for a queue, we're going to only be able to insert things at the end and remove things from the front, we add an additional layer of abstraction that protects us from having to consider the full complexity of what's going on. When we just have these two operations, insert at end, remove from beginning, we don't need to think about, okay, insert at index blah. We don't need to add all these other operations which are like get length. We've simplified the interface to ourselves. We've simplified the set of functions that we have to think about when we're using it. Now, of course, when you actually go and implement a stack or a queue or a list, you do think about the underlying complexities. But the idea is once you've finished implementing it, you should have this layer of abstraction and you never have to think about most of the parts of the data structure again. Those parts are hidden away by the abstraction. So our whole idea here was to abstract the order of accesses away from the order of arrival, and this is what gave us stacks and queues, but we can come up with other forms of abstraction, other forms of representation that will ultimately prove useful. One other kind of abstraction that we saw in yesterday's lecture was polymorphism, this idea of using one function with that works with multiple different types. So like we had our linked lists, we had our data t that we could swap out for an int or for a string or for whatever it was that would work. This is what polymorphism is. To go into it a little more, you can imagine a vending machine as one kind of simple form of polymorphism. The basic interface of the vending machine is put money in get snack out. And despite the overly large prices, I'm actually quite pleased that these things exist, particularly when you're in a bind and everything's closed. But depending on what you have on, depending on what kind of money you have on you, interfacing with the vending machine might look a bit different. So if you have dollar coins, you might put coins in the slot over there. Or if you have a credit card, you might swipe the credit card. Or if you've got your phone, you'll tap your phone and use the PayPass thing. This is an example of polymorphism because the operation of put money in, get snack out is ultimately the same. The machine is just built in a way that it can handle money whichever way you decide that you want to interface with it. Maybe even there's a fancier version out there that accepts cryptocurrency. Super polymorphic vending machine. So polymorphism in computing looks kind of similar to this. If we want to do sorting, we can sort integers, or we can sort words in lexicographic order, or we can sort presidents in order of newest to oldest, or favorite to least favorite. Fun fact, William Henry Harrison up there in the corner was, I think, the president who was in office the shortest amount of time. He gave an overly long inauguration speech, got pneumonia, and subsequently died. So that is your fun non-computer science fact for the day. But one of the interesting things that differentiates, say, the integers from the strings and then even more from the presidents is that it's very clear to us, at least until you go into higher mathematics, to think about what order the integers come in. Well, either smallest to largest or largest to smallest seems to be what it means to sort an integer. But it's not as clear what it means to sort a string. I guess lexicographic ordering that we've seen thus far probably works. And even less clear what it means to sort presidents. Just like when we were talking with, I forget who it was in the audience that we talked about this with, but sorting students. I think it might have been birthday Josh and Laura was the last time we talked about sorting students. So when we use polymorphism inside a program, we have to define what the operation that we're trying to do is and how that relates to the object with which we're trying to interact. In this case, we're trying to understand what it means to sort. But to understand what it means to sort, we have to understand what it means to order something. So we've got this very fancy definition that I picked off of Wikipedia today about a total ordering, which is what we need in order to do a sort inside one of our computer algorithms. And it's got all these different properties. So if A is bigger than B and B is bigger than C, then A is bigger than C. So if 5 is bigger than 4 and 4 is bigger than 3, that must mean that 5 is bigger than 3. So we have all these properties, but for the most part, as computer scientists, at least at this level, we can ignore most of that and just ask this central question. Is A equal to B, A bigger than B, or A smaller than B? And assuming that we define this for our objects, we can then use them in a polymorphic fashion for sorting. So what we ultimately need is something that gives us an answer to this question. Is it equal, is it bigger, or is it smaller? Because it can only be one of these three things, assuming that we want a total ordering, which is this mathematical notion that allows us to construct a full order of our objects. Inside the compiler, there is a special library that gives us access to a whole bunch of functions. And we've seen this already. We've used standard lib.h, string.h, etc., etc. All these are part of a larger library called libc. Now, there are a few variants of this. You don't have to use libc, but pretty much every compiler out there, with a few exceptions, uses it. And just like Linux, it comes with a manual. This is from the libc manual that talks about defining a comparison function, which is ultimately how we're going to implement polymorphism for the kind of sorting that comes built into our compiler. And we're not going to read through this whole definition. It's kind of here for you to check out on your own. But the key thing is that you want to create this comparison function that tells you, that answers this question we just had. Is it equal, is it bigger, or is it smaller, and returns a negative number, a positive number, or 0, depending on the answer. And so assuming that we implement this, it will allow us to use qsort, the built-in C sorting function that we saw in the other lecture when we were building up our suffix arrays. Let's look at that one more time with our new knowledge. So that was somewhere here. I guess it hasn't synced. Insert end. It'll be in lecture 8. There we are, string sort.c. So this was our big suffix array construction to bring your minds back to it, and we tested out a few different ways of sorting our suffix array. So I have the function run tests that tests all our different sorting methods, and somewhere in there we had this qsort function over here. And one of the arguments to qsort was this function here, compare string. Wait a minute, that's a little funny. I gave a function as an argument to a function. Well, this is going to be one of your next key learning points, which is functions. You can have a pointer to a function as well. Functions can take as arguments pointers to other functions. And this is one powerful way of implementing polymorphism on the computer. So qsort expects to get the name of another function or a pointer to that function, which enables it to decide, okay, what is the right way to compare these types of objects? So if we wanted to run qsort with presidents, we could pass it a function, a comparison function, which tells it how to compare presidents. It might be like, if president dot year in office is bigger than, if president 1 dot year in office is bigger than president 2 year in office, return a positive number. If president 1 dot year in office is smaller than president 2 year in office, return a negative number. If president 1 dot year in office equals president 2 dot year in office, return 0. Let's see what we did, how we implemented it here. We have a function compare string. And let's look at the implementation. I have 2 strings, which is the input to it, although these could be 2 of any type. It could be 2 struct presidents. So I could do construct president 1. Let's make that a pointer, and const struct star president 2. And then what we'd do is we would write something like president and in theory, this would work. Obviously, I haven't defined presidents here, so it's not going to. But that is how we can get one sorting function to work with a whole bunch of different types, even when this notion of what it means to sort on this particular type is only partially defined. We have to give this function extra information about the types it's dealing with in order to enable this polymorphism. Now, the syntax for function pointers is a little complex and is a little tricky. To go over it, I encourage you to read the relevant chapter in the book because we're not going to have time for it in lecture today.
There was a question in the chat.
Oh, yeah.
What does const mean?
Const we talked about in an earlier lecture, but it essentially tells the compiler that the argument that it's receiving is not going to be changed by the function that just received it. So for example, with our pointers, this means that the contents of the pointers won't be changed by the function that's running. So a comparison, when you're comparing two things, the comparison shouldn't change the objects themselves because you just want to see how they relate to each other. And so adding that const there helps the compiler to know that and allows the compiler A, to reorder things in a way that makes it a little faster, and B, helps protect you from mistakes in case you're using things that in case you write something in the function that does change it and you've just promised to the compiler that, hey, I'm not changing this, it'll flag that for you and say, wait a minute, you just promised me that this thing won't be changed, are you sure you know what you're doing? And will probably fail to compile. So languages support polymorphism to different extents. Python is very, very polymorphic and is very expressive with regards to this. Yeah. In some languages, you can change what the plus in the language means. You can change what the minus means. C has more restrictions than that. We implement polymorphism mostly using these function pointers. But C does have some built-in basic polymorphism that we've already seen. You can add together using the plus sign two strings. You can add using, you can add 2 pointers. You can add using the plus sign 2 integers. You can add 2 doubles, 2 floats. And so we already have some notion in C that we can use a single operator to act on multiple types. And this is really just an extension of that idea. Unfortunately, for structs, we ran into problems. Some of our operators just straight up didn't work, like equality, greater than, less than. And this is because C doesn't have an easily built-in ability to reuse those operators in a polymorphic fashion for more complex data types. So that's the end of our discussion on linked lists. And we have a bit of time to get into a new topic that Jianzhong will then take over with. And I might even get him to show you a bit more function pointers in that lecture too. So we have a new challenger approaching for our data structure. Linked lists were great when our data is one-dimensional. When things are like in some kind of order, like a queue, like Hamilton tickets, that was great. But there are a lot of things in life that aren't one-dimensional. So I have my friend here who wants to know which of his ancestors lived the longest. He's looking a little gray in the face and is worried about his longevity. So he looks to his family tree. Unfortunately, most of the monkeys I found online were male, but I do strive for equal gender representation in all apes that I display. It was just a little difficult. So up at the top here, we have Naruto, the monkey who is famous for, the monkey appeared in court, claiming that he owned copyright over the selfie that he took, and the photographer who owned the camera claimed that the photo belonged to him because monkeys can't own copyright. Despite the monkey's wonderful arguments, it was very eloquent. The judge ultimately gave the copyright to the photographer. But that is Naruto over there, with parents Rafiki and King Kong. Rafiki was born to Sun Wukong, who is the son of King Louis. King Kong was the parent of Abu, who was gifted to Mojo Jojo and Kala, and Mojo Jojo was born to Donkey Kong. Now you'll note that we don't have a complete tree here. This is because monkeys are really, really bad at genealogy. Some of them have lost their parentage. They don't remember what years they were born. So this is the best that Naruto could do in terms of figuring out his family tree. But he wants to know, out of everyone he knows, who lived the oldest. Well, we call this a binary tree because for every potential link you can have, for every individual, they can have 2 parents. Or in this case, we should be a bit careful here. The computer science term, in computer science, we're not the smartest people. So we call this a tree, but it's actually flipped upside down. So we call the thing at the top the parent and the thing at the bottom the children, even though in this example it's somewhat. For any given node, the nodes that spring off from it downwards are known as the children nodes. Even in this case, we're talking about genealogy, so these are actually the parents. But I'll steer away from child and parent terminology because otherwise this will get confusing quickly. So root, leaves are all the ones at the very bottom that have no children themselves. And this gives us our binary tree. I'll rethink that example next time. Very confusing having the parents being the children. So each of the monkeys lived to a different age, and Naruto wants to figure out in his whole genealogy who was the monkey who lived the oldest. Now, you as people are able to just look at this tree and see what the answer is. It is Kala over there in the corner as 40. But we're already used to our model of computation, the way we think about how a computer looks at objects, and the computer can't see all these bits of data at once. It can only look at one thing at a time and compare it to something else, and eventually try and figure out which of the numbers that it's seen is the largest. And the way it does that, remember you've written this in your earlier computing classes, is by keeping track of what the previous largest number was and then looking to see is the current number larger or not. And once it's gone through everything, then it knows if I've seen everything and I was always keeping track of the one that was largest, the one that I'm looking at now must be the largest. But how do we do this when we're representing our data this way? Well, let's start from the assumption that the only thing the computer has access to at the beginning is the root of the binary tree. This is Naruto at the top. He's the start of our quest. And so that is what the computer is looking at. And some of you might guess that pretty soon we'll be using pointers, and the root will be our first pointer that we have here. This is what it looks like were we to try and implement this structure the same way we did a linked list. It's just like a linked list, only this time, instead of having node t next, we have node t left and node t right, corresponding to the two links on the left and the right of each of our characters here. So what is the runtime to find the oldest monkey if we're doing this as our computer mine? Well, we start with Naruto at the top, and let's do a method by which we go to the child over there first. 33 is older than 20, so that's the maximum we've seen. 27, not older than 33. 14, not older than 33. And we're following the pointers along each time. But now there are no more pointers to follow. So what do? How can we get back to the things that we haven't seen? Yeah, we can backtrack. So we can go back, 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 and we're back at our root again. And now we try the other side. Is 14 bigger than 33, which was the biggest we'd seen so far? No, let's move on. Is 22 bigger than 33? No, let's move on. Is 40 bigger than 33? Yes, okay, that's our biggest. Is 21 bigger than 40? No, okay, let's backtrack a bit. Now, is 34 bigger than 40? No, and now we're done. We've looked at everything, and 40 was the biggest. But what's the runtime of this? And we'll take the microphone this time. Okay, who haven't I spoken to?
Ashley.
Ashley, I have called on you before. Alicia. I don't think I've spoken to you, right?
No.
Great. So you're today's victim.
I'm not sure, sorry.
It's okay, well, I'll help you, I'll walk you through it. So take the microphone. So let's look at how this process functioned. So in order to figure out that 40 was the largest, how many of the items did I have to look through as a fraction of the full set of items? So are there any items on here that I didn't look at? And try and hold the microphone up.
No, you looked at all of them, didn't you?
Yeah, I looked at all of them. And if there are n items, how many things did I look at?
N.
N. So then the runtime would be?
N?
N, yeah. So this isn't that efficient because we had to look through everything to find the largest item. Are there any algorithms that we've seen so far that allow us to find a specific item quickly in a list?
Yes.
Do you remember which one it was?
No.
So maybe this might help jog your memory. Something where we split the list into halves and then looked at each half. Do you remember an algorithm that did that?
Not exactly, sorry.
So I'll give you a hint. This is called a binary tree. Something else that sounds kind of similar. Not ringing any bells? Binary search. And do you remember how long binary search took? It's okay. Binary search took log n. So we know that there are some ways to optimize like a searching procedure, but binary search only worked when our list was sorted. So this is going to give us a little more trouble. Thanks very much, Ashley. You did great. So maybe there's some way, just like binary search worked, where we had some kind of structure already in our thing that optimized our search procedure. Maybe there's some way of like changing this structure up that enables us to do something similar, to improve the runtime of our algorithm by changing the way we structure our data. So poor Naruto, took him O of n to find the oldest person in his heritage. But Naruto is a very smart ape and wants to do a lot better. Obviously, if he took a photo, he's busy writing algorithms on his weekends. So this was slower than linear search and much slower than binary search. Admittedly, binary search is a little more specialized and only works for certain things, not for finding the maximum, unless the list is already sorted. But if the list is already sorted, we know where the largest one is. So not quite what we're looking for, but something along these lines is ultimately what we want to do. Yeah, binary search required building something special. So maybe we can build something special. So instead of having a total ordering that binary search required, maybe we could build a partial ordering of the elements that's faster than a full sort, map that to our tree, and then see if we can take advantage of it to do a much faster search. This gives us not just a binary tree, but a binary search tree. This is a special version of a binary tree, which is just any old collections of nodes with two children coming off. A binary search tree has this property. This is the key property for binary search trees, that the right subtree is bigger than the parent, which is bigger than everything in the left subtree. So I'll say that again. Everything in the right subtree is bigger than or equal to everything in the parent, which is bigger than or equal to the parent, which is bigger than everything in the left subtree. Now, it's also okay to reverse this and flip everything the other way. So make it that the right subtree is the smaller one and the left subtree is bigger. It's just a choice, an implementation choice. Either way works because the structure of the algorithms are symmetric. So here is a construction of our binary tree as before, only now I've reordered things a little bit and put them in the tree in a different order. So this is no longer whose parent was who. This is structuring them according to this rule that we just gave, where so you can see that 14, all the 14s are in the right subtree of 20, and all of them are smaller, and everything in the left subtree of 20 is larger. So 33, 27, 22, 21, 40, and 34 are all bigger than 20. And if we look at each of the nodes, this property holds for their children as well. So it doesn't just hold for Naruto's 2 pointers coming off, it holds for Rafiki's 2 pointers coming off. So 33 is bigger than 40, 33 is smaller than 40 and smaller than 34, but 33 is bigger than 27, 22, and 21. So now we might have a faster way of finding the largest element in our tree, which will hopefully answer Naruto's question a little more quickly. So Angel, I can see you've got a thinking face on, so I'll give this one to you. So assuming we're starting at our 20 over there, how do we find the largest element?
You just have to continuously search in the right subtree, because that holds the larger element.
Slow down a little. I start at 20. Where do I go?
33.
I follow the right subtree.
40.
40. And is there a right subtree to go to?
No.
No. So I'm done. I found the largest monkey. And that didn't take very long, did it?
No.
What would be the maximum amount of time that this could possibly take for any arrangement of the monkeys?
It would be log n as well.
Is that the worst possible that it could take?
Well, if the tree is like not balanced, it would be O of n.
Oh, you're getting quite ahead here onto balanced trees. Let's see what happens. So this is going to take over h, where h is the height of the tree in the worst case. So if we have 5 layers down, the worst this could possibly take for our particular tree is going 5 layers deep. In this case, the actual the actual node that we're looking for is only 3 deep, but potentially if if this was structured a little differently, we could end up where we had to go down that path to find the number 21. So for example, if the question instead of who is the oldest monkey was, is there a monkey who lived to the age of 21, then we would have gone, Angel, do you want to help me follow this through to find out if there's a monkey who lived to age 21?
So you have to go to the right because it's greater than 20?
Yep, it's greater than 20. Is it greater than or less than 33?
Less than. So
less than 33, less than or equal to 27?
Less than 27.
And 22?
Less.
Less?
Yeah.
And so it took us 5 steps. So this gives us an average case of log n. But Angel is right, as this assumes that something about our tree. It assumes that we have a certain knowledge about the way that the tree is balanced. So we can use this same technique, just like we did, to find any value in the tree. But we do have a worst case that's much worse than log n. Do you want to explain what's going on in this slide for us?
So basically, well, the list might be, like if you have like an initial array, it might be sorted already, so that when you're building the tree, the next element is always greater than the previous one. So you just keep on building the right subtree and you have nothing on the left. So in the end, the depth is n.
So the depth is n, which means what's our worst case to find an object in this?
O of n.
It's O of n. This is just like a linked list search. It's exactly the same. And forgive the computer science pun, because this is a tree that is just singular and long, we call this kind of structure a stick. So it turns out that binary search trees decay to sticks in the worst case, which looks an awful lot like a linked list with a bunch of pointers that are going unused. So n items with a height of n, we have a stick, not very good. Optimal binary tree structures to find the best possible way of building these and the way to make them fast is really still an open question. Next week with Janjong, you're going to look at some of the construction algorithms and look at insertion and removal in binary search trees, as well as how to use them. Thank you so much for all these weeks of semester so far. I'm going to see you in about 2.5 weeks and take a lovely holiday. I'll catch you all in the last week of semester. Thanks very much, everyone.